students. Welcome to this morning's seminar. And this seminar is a joint seminar organized by the Graduate Institute of Hydrological Science and Art Department. And today our distinguished guest is Dr. Fung from UC Berkeley. So first of all, I would like to express our very sincere and warm welcome to you.
Thank you very much.
Welcome to our department to give a seminar here. And in the following, I would like to invite Professor Liu to give the introduction of the Professor Fung.
Okay. We also have another distinguished Professor Powell, Zach Powell, also from Berkeley, working on physics, mathematics, and biology. Okay, so what a combination. So I think between two of them, they can cover probably half of the science in the world. Okay, I think I'm going to give my introduction in Chinese anyway. I think Professor Fung understands, so I'm not going to say anything crazy. Please, so excuse me, Professor Powell. I think probably it's easier for the students to understand. So keep them awake for a long breath, or longer than expected. 冯教授他是这个在香港长大，然后呢，在这个去美国念大学，他是 MIT 毕业的。MIT 是应用数学系，1971年毕业的，跟我同一年毕业所以他现在非常有成就。现在OK， 我很高兴能够碰到他。冯教授的先生是这个 Dr. Jim Bishop， 那我在这个Vermont的1年的时候呢，跟这个 Jim Bishop 常常在一起吃午饭，讨论一些学了很多东西所以我们这个，所以我跟冯教授其实并不熟，但是呢，跟他先生是比较熟。冯教授他这个后来就接着在这个大气系念他是这个据我们的那个王才老师说他这个冯教授是跟George Charney George Charney so I don't know this person but anyway that's a big shot 1977年他拿到博士学位，然后博士学位呢，他的博士论文呢得到这个 Rossi Award， 然后他的这个论文题目呢，他的第一篇论文题目呢，我想可能大家听了会比较有感觉，对我是一点感觉。The organization of spiral rain bands in a hurricane, okay, presented at the American Meteorological Society. OK， 所以我们说，它的确是一个这个跟大家都是非常接近、非常同行的。那当然后来，据说他会找不到事，所以找不到事也不用担心的。那这个，所以他先生在Vermont的时候呢，他是在 East， 在 Goddard Institute of Space Science， 在 New York City。然后呢，他就做了一些有趣的事情那当然包括呢，在我们的这个生物宇宙化学方面呢，他也做了一些这个利用这个inverse model 来做了一些这个二氧化碳的吸收的这样的一些研究那引起蛮大的震撼。那当然到后来的时候呢，他就把这个整个的把动力学然后呢这个大气辐射，还有呢生物地球化学三个连在一起。那这一连在一起真的不得了，因为要做气候的长期气候预报，就是要这三个东西还要包括路面的过程都连在一起。那他前天我们开会的时候，他说他花了5年的时间呢，去到了一个 model。OK， 所以就知道说他的确是不是说只是在高高在上自己做这个 director， 而是说实际上他是真正在做这个科学的一个非常认真的科学家。那他在2001年呢就获选为 National Academy of Science member， 然后2004年呢拿到这个 Roger Revelle Medal。OK， 是这个 American Geophysical Union， 这个是大概是最荣誉的一个奖章然后呢又这个选为这个 Scientific American 的50 scientists 等等得奖人数。然后让他这个最大的贡献就是说，怎么样能够把这个非常复杂的这些生物地球化学东西跟物理连在一起那他现在呢是这个 Berkeley 大学UC Berkeley 的 Department of Earth and Planetary Science 的教授。同时呢，也是这个Berkeley Institute of Environment Co-Director， 是 外，它也是这个就是 Department of Environmental Science, Policy and Management。所以呢，它在除了科学，它在整合之外呢，它在这个环境的议题上面也整合了，就是科学还有就是政策以及管理。所以我想我们从今天他的演讲里面会给我们得到很多启示，我们 man 可以做到整个地球的问题。So let's welcome Professor Fung and her talk will be modeling carbon-climate interaction in climate models. Okay, Professor Fung.
Thank you very much for the very warm welcome. It's a great pleasure to be here. I want to talk to you in a sense about what I have learned since I was a graduate student. I always like great cloud patterns, and this is a spectacular, this is off the coast of Mexico, so this is fluid dynamics, okay, so I want to challenge you if you know what Reynolds number flow is, this flow with topography. It is a marvelous case. But what I wanted, when I was a postdoc, when I finished my thesis, my advice to Charney, I think some of you know, Charney did the very first numerical weather forecast experiment on the ENIAC computer with 10 words of memory. And it took them 24 days. It's a barotropic vorticity model. But anyway, so when I finished my thesis, when I did my thesis, I had to learn Fortran. And Charlie said, no, you're not going to do a numerical thesis. You have to solve one problem in your life analytically. Okay, so you'll be working with computers later. So then when I finished my thesis, he told me that I had to go learn something new. So I went to Goddard and started learning the mixed there, the ocean, to learn about oceanography. And then I was commuting between Washington and New York, and Charlie came and said, you should not do that, go home. And I said, but nobody knows Navier-Stokes. Okay, so then he said, learn some chemistry, you're married to a chemist. And so I started learning the carbonate system from that point on. So what I want to talk to you today is about the coupling the carbon system with the climate system. This is familiar to everyone here. Conservation in the atmosphere, we have conservation of momentum, the Navier-Stokes equation, conservation of mass, the gas law, and conservation of energy, water vapor. So when numerical weather forecasting is an initial value problem. Okay, so you basically look at the momentum equation, you get the wind, and then you embed the temperature, and you embed water vapor, okay? But in climate, where we spend most of our energy is on the energy equation. Okay, so to get the energy equation, we need to get the short wave forcing, the long wave sensible heat, and latent heat, so that changes the temperature. With temperature, we change the pressure. With pressure, we change the pressure gradient, etc. And obviously, water vapor here. So the link in the climate system is this very short thing, where the short wave radiation, how much energy, solar energy hits the surface is a function of the clouds, the aerosol, the atmospheric composition, and similarly for long wave radiation, it's temperature, humidity, CO2, all the greenhouse gases. So to get the climate, we have to predict, we have to know the distribution of all of these, get the water vapor, get the temperature, and then we can go through the gas law and go back to pressure gradient, and then we're on familiar territory. Okay. So the climate forcing, when we talk about the climate problem, this is, the rogues gallery. These are all criminals, okay, of climate change. So climate forcing we express in terms of what Bermuda squared. So you can do the radiative transfer calculation and say CO2 in the atmosphere increased from the 1800, this is a perturbation, from 280 parts per million now to 380 parts per million. That represents a forcing of 1.4 watts per meter squared per surface. Okay, similarly for methane, we know the absorption, the absorption lines and the strength of the absorption lines, and we can calculate the radiative forcing of all for everything. So here are the greenhouse gases, CO2, methane, CFCs, tropospheric ozone, nitrous oxide, okay, and they contribute to warming. This is since 1800. So we're looking at the perturbation energy cycle here. And when we think about climate, not the background climate, but the perturbation climate cycle. And then on the other side, we have the changes in composition, the land cover that will influence the solar part of the radiation, so that aerosols have more. We often with aerosol in the atmosphere, and then the aerosol as acting as cloud condensation nuclei will change the cloud formation processes and cloud lifetime. Okay, similarly for land cover change, there's change in albedo, the reflectivity of the surface. The sun is very indirect, and the volcanic, this small change due to volcanic eruptions, aerosols, and they last about 3 years. So when we look at the climate, first is to look at the forcing, then we look at the feedback, and the feedback, basically, principal feedbacks are through the hydrologic cycle. Most obvious is if we have a warming, then the warming would melt the snow, okay, it would melt the snow, that would increase the absorption of solar energy. Warming would also cause evaporation of water from the ocean, and water vapor is a greenhouse gas, and so that enhances the greenhouse effect. And so the dial, if you will, the dial in the climate system is in the cloud cover, and so clouds more reflective, clouds over the ocean will make the ocean brighter, so that reflects more sunlight and decrease the energy absorption. This is a very complicated problem because if the clouds are taller rather than more horizontal coverage, then the clouds would radiate at a colder temperature, okay, that would contribute to warming. But the net effect of the distribution of clouds is to decrease, and that's a negative feedback due to the clouds. So when we think about the climate problem, yes, there's changes, human-caused changes, increases in the greenhouse gases, changes in the albedo, but the feedback is totally tied to the hydrologic system. So since now we have released the 4 IPCC, so in the whole, in the last 20 years, there's been a lot of progress made with climate models. So this is an example where we can capture the changes, in the system. So this is the perturbation departure from the anomaly. So the black line is the observed temperature increase globally, average temperature, and the model, the spread, this is an ensemble, so the mean and the standard deviation of the model calculations here, so we can capture the variations, most of the variations in the climate. And there's still puzzles, but you can see this is the eruption of Pinatubo is here, this is Ajichon. Okay, so after every volcanic eruption, there is a natural experiment, if you will, for us to test our climate model, and we can simulate those fairly well. And the ocean, always a difficult part because of the lack of observations, we can also simulate the ocean heat content. Okay, so this is from the observations, the red line is from the Brandon tracers in the ocean, and so the history of changes in the heat content of the ocean is also very well simulated. So in a sense, this is nice because you have confidence in the physics, okay? And then it varies, okay? Low order confidence. Okay, when we look closer, then we find things to do. So the recent models, I work with the NCAR model, the National Center for Atmospheric Research in Boulder, Colorado. And so the recent population from the NCAR model, also we can simulate extreme events. Okay, here on the left, on the top panels are the observed heat waves. This is for North America and this is for Europe. Okay, 2 events, and so this is the composite simulation from the model. Okay, so we are beginning to be able to say not just the global average, but have some confidence in regional scale. Not San Francisco versus LA, but regional scale, broad scale changes in climate, in the climate extremes from the climate models. So from the models we predict intense heat waves in the future. So one of the challenges of climate projection is how fast the climate will warm. And I'll start here. The lower panel is supposed, we're increasing CO2 all the time in the atmosphere. But we just do a thought experiment, hypothetical experiment, and say suppose the CO2 remain constant at 380 parts per million. Suppose. Okay, we can't do it, but let's suppose. It's still warming in the pipeline. Okay, because there's CO2 in the atmosphere, there's down radiation, it evaporates water, greenhouse gas, okay, and that heats the oceans on more, etc., etc., etc. Okay, so the first initial warming is due to the CO2, but then there's magnification, there's a feedback due to the water. Okay, so it takes a long while. This is about 100 years to reach equilibrium. So when we look at the difference between the end of the century, the end of the 21st century versus the end of the 20th century, there's still warming even though we have not changed the CO2 concentration. So obviously if we change, and this is a business as usual scenario, the CO2 increase in the model from 380 to 680 parts per million, okay, then there's obviously warming everywhere. So what I want to talk about today is a review of the carbon cycle and what we do to couple well, I told me this is like 5 years of my life, coupling the carbon cycle and the climate model and the experiments that we have done. So many of you are familiar with the CO2 rise. This is the concentration at Mauna Loa Observatory when Dave Keeling went to the observatory and started measurement. Okay, so you see the increase from about 315 parts per million here. Now we're over 380 parts per million. Okay, very clear increase. Superposed on top of the increase are very regular cycles, seasonal cycle. So there's a peak. This is in May. Okay, the photosynthesis starts in the northern hemisphere, so CO2 goes in the plants. Okay, and then this hits bottom in October, and it comes back up. So decomposition, okay, releases the CO2 back to the atmosphere. So we have the secular trend, okay, increasing, and the very regular seasonal cycle. But if I go back to the secular trend here, and look at the budget of CO2, then this is a petagram carbon per year, 10 to the 15 grams of carbon per year. The emission, fossil fuel emission, is here, okay, and this is the time derivative of the CO2 curve. Okay, this is dCO2 dt here. So what you see here is that about 50% of the emission is in the atmosphere. That means about 50% has gone into the land and the ocean. Okay, this is, so not only that, when you look at this, the emission is fairly constant, whereas the land and ocean sinks, okay, is very variable and very sensitive to El Niños and Pacific, all the natural climate variations. So the question we ask is, since the ocean sinks, okay, the land and ocean determine how much remains in the atmosphere, then will the warming change how the land and ocean would work and change the CO2 increase and change the climate? Okay, that's the question I addressed with this. Before I go ahead, I just want to show the equations. The carbon cycle is here on the lower right. So I mentioned before that the plants take up carbon. Okay, so the plants breathe in and the microbes breathe out, the decomposition breathes out. So this is about 100 petagrams in and 100 petagrams out. Okay, the ocean also 100 petagrams in and 100 petagrams out. There's exchange with ocean, there's biology, there's exchange with the deep ocean. Okay, so superposed on that is a fossil fuel emission. Okay, so this is, remember, this is 100 in and 100 out, 100 in and 100 out. So what we're taking from the geologic carbon cycle is now of order 8 petagram, 5, 6, 7, 8 petagrams in, and so some of it has gone into the land and some of it has gone into the ocean. So looking for 1 or 2 petagrams, okay, remember, if this is 5, 50%, that's 2.5 petagrams have gone into the land or the sea. Okay, so looking for that 1 or 2 petagram in this 100 in and out is very difficult. So what we do here, first is to represent a carbon cycle. So the atmosphere, so this is just an accounting exercise, okay? So this is with the advection, so that the inventory and the atmosphere changes because we have fossil fuel emission, we have deforestation, and then we have exchange between the ocean and the atmosphere, exchange between the biosphere, terrestrial biosphere, and the atmosphere, and this turbulent mixing. Okay, similarly for the ocean, there's changes just with the atmosphere, and locally there's biology that produces, okay, loss photosynthesis removes carbon by this reduction, minimalization. Similarly, for the land, we have a different, for trees, for tree trunks, for tree roots, okay, and leaves, there's some allocation of flux. Okay, what the atmosphere loses is allocated to these, and then each one has a turnover time, a lifetime. You know how long leaves hang out on trees. You know how old trees can get. Okay, so that's represented as a turnover time here, and similarly for the soil carbon. I'll go through that again. So, but from a modelist point of view, okay, what I really want is here the atmosphere has to start pre-industrial atmosphere 280 parts per million of 560 petagrams of carbon, and this exchange here. So the biosphere has 2,000 petagrams and it has turnover time of decades. No, you think about trees, okay? Decades. Whereas in the ocean, there's a huge reservoir of carbon, okay, and the turnover time is of centuries to thousands of years. So what we want to do is to put in fossil fuel and then see how the system interacts. Now look at this pool, okay, these pools are huge compared to the atmosphere. Okay, so what we worry about is could the warming destabilize these pools, okay, and accelerate the warming itself. So what I want to talk about are the terrestrial and ocean carbon cycles. So again, what I said was, we're familiar with looking outside. Okay, trees photosynthesize, okay, they remove carbon from the atmosphere, and they breathe out, okay, through, this is autotrophic respiration, plants breathe out CO2, but then the turnover time, the lifetime of leaves, of stems, of root systems, and so these decompose, okay, and then this is heterotrophic or microbial respiration, the liquor on the ground decomposes, okay, so this is the organic carbon, okay, worked on by the microbes and the CO2 is released back to the atmosphere. So on average, this is the balance. When I started this, when there were no satellite data, when there were no data whatsoever, I call this my sneeze function. When there was pollen in the air and I have allergies, and this is my rock function. Okay, so when you go hiking, you know how much litter there is on the ground, how long, how old the litter is. Okay, so now we have satellite data. We don't have to do things. Okay, so, but in terms of a model, again, okay, we have a schematic. I write the equation. In terms of the model, then this is the photosynthesis, okay, the gross carbon productivity. So we have the autotrophic or the plant respiration, and then this goes to the, so the net primary production is allocated to leaf, roots, and woods, and so the leaf have a certain lifetime, and then there's decay into different pools. Don't worry about the words. It took me a long time to learn the words. But what it is think about this leaf of stems and easier to decompose and more difficult to decompose. Okay, so different time constants for these processes. Similarly, the wood, and the wood goes to the coarse woody debris, and that has a different decay time constant. Okay, and then these go into a longer term pool, and they act on by the microbes. So it's microbial respiration jumping to the next is microbial respiration. That is heterotrophic respiration. So how this is coupled to the climate system is through leaves. Okay, the atmosphere really doesn't care about the root. Or, there's something about the root, the height of trees as a roughness for the momentum exchange. But most importantly, the leaf, the leaf area index, or what is the area of leaves per area of ground. Okay, so meter squared per meter squared alters the albedo of the land surface. Okay, that alters the energy exchange. Also, how many leaves I've got determines how much photosynthesis I can have. Okay, and therefore how much carbon I can accumulate. But what you learn from high school also about stomates, or leaves that are openings. Okay, through the stomates is CO2 in and water out. Okay, this is the most important feedback between the coupling between the climate system and plants is through the transpiration of water. Okay, plants transpire in the same way we sweat, for cooling purposes. Okay, so when the plants close out, the stomates, not only are they not growing, they are cooking themselves. Okay, so what we have, I won't go through all the details, but what we have is we actually compute the stomatal resistance, okay, as a function of ambient temperature, humidity, okay, and so when the plants close, then we have less transpiration and the water and the ground heats up. This is a very important process in coupling the atmosphere to the land. And when we look at data for the droughts, my students have been analyzing droughts. When there's a drought, it's not just the moisture from the sea, but also the plants, the plants are not transpiring water, not recycling water. Yes?
I'm thinking that the opening and the close of the leaf may also depend on chemical concentrations.
Oh, yes.
For example, if you got more ozone there, then the leaf
Yes. Oh, yes. Yeah.
So
we don't have it yet. This is the first. The next model will have the ozone and the interaction and the emission of volatile organic carbon and everything else. Okay, this is the first very simple schematic. So we're just coupling the carbon, but through the leaves, okay, and through this little opening, okay, the leaves and the opening of the leaves, we couple the carbon cycle with the energy cycle and the water cycle. For the ocean, this is my favorite picture of the waves. This is a satellite picture, so you see very clearly that when there's chlorophyll, the green line here, when there's chlorophyll is when there's upwelling. Upwelling brings cold water. Okay, so it's always cold water and upwelling. Okay, so the productivity is upwelling brings up nutrients and it also brings cold water. So the biological carbon cycle we have is just, it's very simple. We upwell nitrates, we upwell nutrients into the surface where there's light. Okay, so then there is particulate, O is organic matter. Okay, so the organic, so there's recycling here, then it goes into dissolved organic matter, these guys, and then the sinking of organic matter. So basically, all it is, it took me a long while to get through the language, it's basically biological stuff, it's organic stuff, okay, so in the ocean, I think meat and bones, okay, so there's organic matter and there's inorganic matter. Okay, so then there's particulate and dissolved. Okay, so there's always the transformation. In the ocean, the biological cycle changes the dissolved carbon concentration by here going from inorganic carbon to organic carbon and back again here. Okay, so this is the growth and the decay on land. From the atmosphere's point of view, and this is an apology to biological oceanographers, then what I care about, the dissolved inorganic carbon species, the carbonate chemistry is reversible chemistry. So we have three species, CO2, bicarbonate ion, and carbonate ion. And the atmosphere doesn't care about all this. Okay? The atmosphere only cares about the CO2. So if there's a partial pressure difference between the air-sea interface, and so CO2 go in and out without based on the difference, that partial pressure difference. And this is only 1 to 2%. But what I need to do is to say, how does this guy change? This is carbonate chemistry. The dissociation constants, well known as a function of temperature and salinity and pressure. So what we need to know is not just the circulation that is advecting the carbon around, but how the photosynthesis, so this is removal, what I said, the loss term, okay, the removal of carbon, conversion of inorganic carbon into organic carbon, and then the return, okay, the remineralization or the conversion back from organic to inorganic. Okay, so what I want you to remember is here is that what we need is upwelling, okay, to bring the nutrients up. And when it's upwelling, I also bring out high concentrations of carbon. Okay? So then it depends on what the biology is doing that determines the concentration of carbon, and that determines what the atmosphere can see. So I go next to the coupling part. So we have very simple models. And when I started this, all those models existed. So the coupling is difficult, and I'll spend a few minutes on it because I can still not, I've not yet recovered from this exercise. Is that the carbon is adjusted to the climate. Okay, you have seen the Vostok, the ice core, okay, CO2 and temperature go up together. So any error I make, okay, in the carbon system, I'm going to change the climate. That means I'm going to go into a different state. Okay, and I can tell you I got into an ice age in 10 years because I had a sign error. And all sorts of things like that. Okay, apart from the units and orders of magnitude of what which goes up and which goes down. Okay, so then part of the issue is adjust to the climate, but I'm in the model world, I'm not talking about the real world. Which model, which climate am I talking about? Okay, so then what in the spin-up is to find the distribution that's in equilibrium with the model climate, okay, not the real climate. So what we do then is to attach, if you will, rubber bands between the carbon system and the climate system. Okay, and the rubber bands come in 3 flavors. Okay, the first one is tracer, I call it tracer. So this is, the climate system doesn't see the CO2. Okay, you can treat it as any tracer. Okay, so then we have tracer CO2 that varies 3-dimension. Okay, so then it's a diagnostic. Am I getting the right fluxes? And can I repeat the monopolar CO2 cycle? Can I repeat the dose-out? All the major things. The second is the biogeochemistry CO2. Then this is what drives the fluxes, and it's the same as this. Okay, except we take the surface value. Okay, this is 3-dimensional, fully 3-dimensional. We take the surface value to drive CO2 into the ocean, and this is what is sensed by terrestrial photosynthesis. Okay, the last one is obviously what we care about is coupling between the carbon system and the climate system. Okay, so the second one I just want to point out. Here, the biogeochemistry CO2 is what would link the land carbon system, the atmosphere, and the ocean, okay, through this. Okay, and this is linking the whole thing to the climate system. Okay, so I have 3 rubber bands, and I will relax them one by one. Okay, so the spin up, and this is what took me many years. And this is everyone, I carry forward, I predict leaves, I do everything in 20-minute time steps, and when the model crashed in year 163, like what did I do wrong? Okay. And so what has been exciting about this whole process, you realize that, oh my gosh, is that what went wrong was that I had a negative square root, and the negative square root came from the ocean chemistry, and it turns out that the climate people forgot. We had a miscommunication about the inland seas. Okay, I did the chemistry in the inland seas, but they never tracked the salinity budget in the inland seas. Okay, so from the climate, you don't care about salinity in the inland sea. You just need to know the source of water. Okay, but I was doing chemistry, and they never looked at it. Okay, so that was a very, so we have gone through many steps like that. Okay, just to correct, so what the climate model people didn't care about, now they have to care about. a learning process on all sides. And so what we have then here, is we couple the land and ocean are spun out separately, and then we put them together, and now only the tracer, okay, so that the land and ocean are seeing the same climate, okay, and then this is going for 300 or 500 years, and then we let go of the next one, so now this is the coupled physics, okay, but not yet coupled to the climate. In the last step, we let the climate, okay, we let the whole thing run free. If we imagine I was a nervous wreck, okay, and so this is, I'll show you examples of the tracer CO2. So this is case where we have specified fossil fuel emission. 96% of the fossil fuel emission is from the northern hemisphere, and so we can see very clearly the hotspots of emission. Okay, and you can see very clearly also the interhemispheric exchange. Okay, the ITCZ, the intertropical convergence zone, is a barrier to the exchange. So that what happens is that you release CO2 in the northern hemisphere, the southern hemisphere goes up, so they go up together after a while. Okay. So you can see here in terms of height, latitude, south pole to north pole, here is the emission. So the convective mixes is up. So you can see the ITCZ, the dropping. The barrier to interhemispheric transport, and so the CO2 crosses to the southern hemisphere in the winds a lot.
So the initial condition of the tracer CO2?
Tracer CO2,
Engineers?
yes. It's, we specify 280 parts per million, but it takes no time to spin up. Yeah. Because the north-south gradient is only 1% of the average. So for the climate people, they don't care. They only want a number. And so I make my living out of the stuff that climate people throw out. So the little wiggles, the 1% that they don't care about. But the 1% is very important in terms of understanding the processes of the carbon cycle. So here's a figure of the dissolved inorganic carbon. So this is showing the model here and the observations here. So again, in the Atlantic, what we see very clearly is a depletion, lower carbon in the surface and higher the depth, because there's biological removal of carbon and return of carbon at depth. But what we also see is the conveyor belt, the thermohaline circulation transporting carbon from the Atlantic up to the Pacific. So we see carbon, okay, so we see very much the large-scale advection, okay, as well as biological processes determining the distribution of carbon and in turn determining what the atmosphere will see. Okay. Leaf area. I just picked plots to show. I've got so much. Okay. So and I gave myself little silver stars because there are no observations. So I think this is a reasonable plot. I predicted leaf area. And so I get more leaves in the rainforest and fewer leaves, no leaves in the desert, and that's things like that. So this is like I can sleep better. It's not like saying I did fine. Okay, I can sleep better. That this is a reasonable simulation of boreal forest and other features, familiar features. So the issue we have, even though I have a reasonable looking carbon, and this is all from the fully interactive system. Okay, the issue is one thing to get the climate, to get the mean temperature, the mean precipitation. We all know from, it's difficult to predict the El Nino, it's difficult to predict the perturbation. So this is where the challenge is how are these processes sensitive to climate. So I'll show you now results of the control run and go into the 21st century. This took 6 months on the computer. Okay? And because it took so long, I started on the crane, which was about to be retired, and I said, please let me finish the run before you retire the computer. Okay, so this is a 1,000-year run, okay, at 10 or 15-minute time steps. I go through the diurnal cycle, I go through storms, I go through everything. And everything is now plotted in terms of the same units in carbon changes in the carbon inventory. Okay, changes in the carbon inventory. So the atmosphere obviously varies, the 5 ppm range, and this is climatically not significant, so that's nice. Okay, but the atmospheric variation, because the 1,000-year run has natural climate variability in the bubble, in the system, then the changes in temperature precipitation would drive different photosynthesis and decomposition rates. So the imbalance between the terrestrial system changes back the atmospheric CO2, okay, and that changes the ocean. Remember, the turnover time of carbon on land is of order decades. The turnover time of carbon in the ocean is hundreds to 1,000 years. So the land carbon is more variable, and the ocean carbon variability is much smaller. Okay, an order of magnitude smaller for the ocean. Okay, so this is really great that we have a control run. So what we do, the other thing about the control run, and I'll come back to why, is to look at the correlation between temperature anomalies and soil moisture anomalies. Okay, I don't look at precipitation because plants need soil water and not just precipitation. Okay, so this is a calculation of soil moisture in the model, and this is still a puzzle we have not understood. Is that there's a positive correlation in northern winter in the cold places and the negative correlation in warm places. Okay, this is northern winter, northern summer. Okay, so this means that when it is warmer, it is wetter, or when it's cooler, it is drier, whereas the negative here, and the negative correlation is warm, dry, or cool, wet. Okay, so why there is, what determines this change in correlation, we still don't understand. Is that critical? This is, in the dark, thick line is a 0-degree isoplane. Okay, so we still don't understand it, but this is what we've got. So what I'll go through is the experiments in the 21st century. So we specify now we have got a control run, a stable, very important, a stable control run. And so what we do now is to put in the fossil fuel emission, specify the fossil fuel emission, and then let the system adjust. So the emission, we have historical emission for the 19th and 20th centuries, and then for the 21st century we do 2 scenarios, but I'll mainly talk about the A2, which is the business as usual scenario. So the experiments we do, and now the terminology is such that coupled means the climate and carbon system are coupled, because this is fully coupled everything. We have land, ocean, ice, atmosphere. So it communicates with a flux coupler. And so in this particular context, coupled means the climate system and the carbon system are coupled, and uncoupled means that I'm using the control climate. I specify the radiative CO2 will be 280 parts per million. Okay, so I'm just looking at the carbon system with the increase in fossil fuel emission, how the CO2, what would be the CO2, and what the climate coupling would do. So this is again a repeat. I start off at somewhere, at 280 parts per million. We release fossil fuel. This is the red line. We calculate the land and ocean uptake, and then the residual atmospheric CO2 is what is radiatively active. Okay, and so this is obviously a fraction. So either radiative, so CO2 fertilization I will come to in a minute. So on land, in commercial greenhouses, they increase CO2. They give it a lot of light and nutrients and water, and they grow flowers, and everything grows faster. So there's an expectation that CO2 could stimulate photosynthesis, okay, and store more carbon. But on the other hand, photosynthesis, biological material, organic matter, needs also nitrogen and phosphorus. Okay, so in the open, in the natural system, where you're not adding fertilizers, there could be a limit to how much CO2, the increase in CO2 could fertilize photosynthesis. So formulations that bound the two. Okay, we don't have observations to say where things would be. So let's start here. So if I have the present day climate, no climate feedback, no CO2 fertilization, the green line is photosynthesis and the red line is decomposition. Okay, so the two fluxes. So you can see there's variation because the climate varies. Okay, and some years there's more photosynthesis than decomposition, and other years there's more decomposition than photosynthesis. Okay, so you can see the variation here ranges about 2 petagram carbon per year. Now, if we keep the same climate, if we keep the same climate, but let CO2 fertilization goes. So this is the other extreme. Then you can see photosynthesis will increase, okay, and decomposition lags behind photosynthesis. Okay, so there's storage of carbon. And so if we have just climate by itself without the fertilization, this also stimulate growth because some places is warmer, earlier growing season, okay, more water in some places. So there could be favorable growing conditions, so there's a trend in photosynthesis even without the fertilization. Okay, so when we do the whole thing, then the question is, what is the range between this? Okay, so these are the two endpoints in the fertilization experiments. So I'll focus on the fertilization arm. So what I showed before is, again, this is the growth and this is the respiration. Okay, CO2 out of the atmosphere, CO2 into the atmosphere, CO2 into the biosphere or out of the biosphere. So the difference is the land is what is stored. So when you look at this, then you see there's an increasing sink, but then it flattens out. Okay, so the slowing down is related to changes because we're letting CO2, okay, it's related to changes in the hydrologic cycle, and I will into that a bit more. So what happens is, what I said is not just the temperature is increasing, precipitation, this is global, then the soil moisture depends on where we are, there's precipitation, but evaporation increases with temperature. Okay, so the soil gets drier in some places and moisture in other places. And this is where, when it's dry outside, things don't grow very well. Okay, so that's what we also have in the model. And so the carbon sink is the changing, the flattening of the carbon sink is related to the soil moisture. And this is another way of looking at it. We looked at it before in terms of the 1,000-year run. Again, we see it in the change in the coupling that where it's warm, wet, okay, high latitudes, where positive correlation, and in the tropics and warm places, in low latitudes where the whole world gets warmer, we expect the low latitudes to get drier. In terms of soil moisture, okay, not in terms of precipitation. Okay, so this is the income and the outgoing. So the growth, this is the regression of the change in net primary production versus temperature. So what we see is the feedback, I showed you the NPP is increasing. Okay, here it's saying that the change is, there's less increase, okay, with the warming when the coupling because of the soil moisture. Okay, so because there's a decrease in soil moisture, then the NPP does not grow as fast as in the case when we have present-day climate. So we look at the storage of carbon. Then in the tropics, the same story again, warmer, dry, we decrease the growth, there's less above ground biomass. Okay, and then because there's less growth, there's less litter. Okay, and then it's faster because it's warm, it's faster decomposition, there's also less litter, there's also less carbon on land in the tropics. And at high latitudes, the opposite obtains, because the high latitude, we are warming, but also the soil is getting moisture, CO2 is higher, so everything is happy. Okay, so we have warm, wet, and increased photosynthesis, more growth here, and also more litter, but it's faster decomposition, so the soil carbon is a decrease in soil carbon. When we go to the ocean, here is the 21st, the run, not the Anyway, from 1800 to 2100, temperature increases compared to the control run, but because we're warming the surface, we're warming the ocean, then the North Atlantic, the solar haline circulation slows down, okay, and there's less export production. So the ocean, remember the stratification, the ocean becomes more safely stratified, okay, so the upwelling, so there's less entrainment of nutrients to the surface, not upwelling, but entrainment of nutrients to the surface, so there's less productivity in that CO2. So at the end, the ocean is also reduced ocean uptake, not just because of solubility difference, there's also slower, less mixing to depth, stably stratified, and what I don't have here is also the ocean is getting more acidic, and the carbonate chemistry pushes to the CO2, okay, so there's more outgassing based on the acidity of the ocean. So the change in ocean storage due to the coupling, the ocean of August is increasing in storage, but because of the climate coupling, the increase is less, and you can see where it is less, where the thermohaline circulation. Okay. The international, what I showed you is part of an international project called C4 coupled carbon cycle climate model intercomparison project. So there are many models, international models, and here are the atmosphere models. This colored in yellow are the general circulation models, not colored are models of intermediate complexity. Okay, so in the land model and the ocean model is also various degrees of complexity. We calculate some models, calculate some model conductors. Here in the income model, I've got 9 solid pools, other people have 1 solid bucket. So basically, what it says is that I have 9 solid pools in different turnover, so the litter decomposes faster, the wood goes slower, whereas in the Hadley model, they have one huge, they have the same inventory as I do, but anytime climate changes, the whole thing would go. Okay, so imagine it's like the ocean, instead of being stratified, you have one box ocean, the whole thing. So what we get here is the range between the Hadley model with one big salt bucket, okay, and me down on the bottom. So what it is saying that there's and this is a huge number, okay? The difference between models, this is a huge number. Okay, it upsets people who want to use this for prediction, but it makes us very excited, So why is Peter Cox's model doing this? And it turns out that the difference is not just the climate model sensitivity. The Hadley Center model has a climate sensitivity of about 3.5 degrees. I used an old model that has a very low climate sensitivity of about 1.2 degrees, so that the terrestrial system and the ocean is being kicked much harder. Okay, the climate is kicking the carbon system much harder in the Hadley model than in the old income model. Okay, so the response is slower. But also the time constants here is that I store as carbon. Okay, so of the salt carbon difference. But the range here all comes down to, remember my line of where the line between the warm wet and the warm dry is. Okay? So that line varies between the carbon, between the various moles. Okay, so that who grows, who has more CO2 out, depends on that line. So in the Hadley Center model, because it is so sensitive, the climate is so sensitive, they dry up the entire tropics, the rainforest dies, and all that carbon comes out. Okay, so this is the demise of the tropical rainforest because they have a very sensitive climate. So this is very, this is the first time we've done it. The conclusion, and this is in the IPCC Working Group 1, Chapter 7, is that for the present day, this is the fraction of the fossil fuel that remains in the atmosphere. So what we have is for 2000, it's about 45% of all the models. And so it increases. Okay, so basically the oceans, even though we have a large range, all the models have less uptake by the ocean, less uptake by the land, and more faster increase in the atmospheric CO2. So I won't go through this, but all of us have temperature increase and temperature increase, and you can see the relationship, and this is the Hadley model here. So the story from all the model calculations is that it accelerates the warming. The CO2 is increasing faster, okay, because the land and the ocean are not storing the carbon as well. So the uncertainties here is impact on the airborne fraction, how much remains in the atmosphere. So all the models expect an increase in the airborne fraction, and this range is because in the Hadley model, the demise of the desiccation, the drying of the rainforest. Okay, so all these, the decomposition and everything else increases the fertilization, and it increases the atmospheric CO2. What could decrease is the fertilization, and that's really uncertain. Okay, and the ocean response to CO2 is something we don't really know. So in summary, what we have from all model calculations and all the data, and with the new IPCC report, global warming is real and happening, and our prediction is tied to the hydrologic cycle, is that the drying of the tropics especially reduce the carbon uptake and accelerate global warming. The stable stratification in the ocean, the acidification of the ocean, also, and everything else. So the physics, basically we say the physics of the system drives the biogeochemical carbon system here. Similarly in the ocean, the physics of the ocean changes how the biogeochemical cycle operates. Okay, it changes the biological cycle, and that also accelerates the warming. So I didn't show any result about this. I did, faster, when we have faster emission, then there's a bottleneck to exchange in the ocean in particular, okay, the thermal time. So it's faster than the bottleneck, then it's also accelerating global warming. And so I think many of you have seen the pictures of the destabilization of the glaciers. That's also accelerating global warming. So if you look at the IPCC report that came out in February, those are out of date. Okay. For my results to be included in the February 2007 report, I have to have the paper submitted by May 31st, 2005. That means I have to have all my calculations finished by December 2004. Okay, that means I have to have the model done. Okay, so right now we are very worried about the next IPCC. Okay, so basically the IPCC, the process of the IPCC means that it is not the most current science. So the IPCC projections are slower, and the uncertainty here, especially for the terrestrial system, is the hydrologic cycle. How water goes, and it's not just rainfall, but it's soil moisture, how the water percolates into the ground, how the plants access the water, and stuff like that. Just want to end on what we're doing next. We finished the first round of the carbon system. I just presented this to you. The next round, we have new physics in the system, but we also have added a nitrogen cycle for the land, and disturbance, fires, and in the ocean, now instead of very simple nitrogen dynamics, we have an ecosystem dynamics in the ocean. So we have iron, the ecosystem sensitive to iron, to silicate, and other micronutrients. So we have macro and micronutrients of different species. And so this is fifth. This should be fifth assessment. We've done the fourth. So then the next phase is to add dust through the system and have marine productivity respond to the iron content, okay, and then coupling. And what we have also is active chemistry in the atmosphere. So the question about ozone will be there in the next round. So I'll stop here. Thank you very much.
Okay, any questions?
It has been great fun for me.
I'm sure something, yes.
Yeah, from your conclusion, I think the hydrological cycle is very sensitive to the climate signal. However, the resolution in your GCM might not find enough to resolve the detailed protection and the specific microphysical precipitation process. So you compare your hydrological cycle with your past hydrological result from satellite or any kind of radar data?
The issue really is an issue of physics. There are no observations of soil moisture. That's it. Okay? We can do so. I can tell you that the physics of this model, I ran it at T31, which is a closest resolution because I need the time, the 1,000-year run. So that is about 3-degree resolution, T31. The same model, or more recent version of that model run at T170. Okay, that's like half-degree resolution. Anyway, so it's a very high resolution model. There's still issue. You can do the precipitation because of flow topography and all that. You can do the precipitation better. There's still issues with precipitation at the edges because we're still using a single coordinate system. Okay, so the pressure gradient force is not very well done in the single coordinate system. But bottom line is soil moisture. Soil moisture is really a challenge. Okay, we do runoff and we have very crude schemes for river runoff, very crude. The residence time of water in the soil is an unknown. The texture of soil is based on very crude estimates. Okay, so there's a large component. There's a new satellite, the gray satellite, using the gravity measurements, changing the loading. But the resolution is great for the Amazon, okay, but the resolution is 250 kilometers. Okay, so you really can't do a good test of the hydrologic cycle. I just started a new project to do measurements, which is a challenge for me. So to do measurements, I'm actually instrumenting 2 watersheds in California. One is steep topography, one is much gentler topography. One gets the first storms from the Pacific. The other has, not this year, but last year had 18 feet of snow and spring melt and different hydrologic cycles. So we're testing all of that with new measurements. But getting rainfall is fine. Okay, there's still challenges in getting rainfall, but after we get rainfall, it's not just evaporation, but how the plants access the water, how the plants close the stomachs, and now the deep roots, in the Amazon they found deep roots, so the wet dry season in the Amazon could be partially determined by the rooting, by the plants. If you look into the Amazon, if you look at the wet dry season in the Amazon, it is not, there's a large east-west variation in that. And we're trying to figure out why is there such a large east-west. And this has to be related to vegetation, how the vegetation accesses the water and recycles the water. So that's a real challenge because we're lacking data.
Compare that video model result with the CO2 measurement from
Oh yes. Yeah, all of that got done before. I didn't have time to show it. Yes.
You are able to reproduce the crossway and also the...
Oh yes. But that doesn't say much because offline I've been writing papers about the missing carbon. So the mechanisms for the missing carbon is still not clear. Okay, so being able to reproduce from a lower is fine. I can do the seasonal cycle, I can do the increase, just by fiddling with how much CO2 fertilization I've got. Okay, but that doesn't mean that I've understood the processes properly.
I don't get it. You say by figuring, so you need to do something in order to get you comparable?
No, we compare very well with the Fung-Modeling. I can show you later. We'll get the seasonal cycle, we'll get the second trend, we'll get it.
The other question I have is about your model leaf area on the Central Asia. Don't have to do it now.
Yeah. I have to go and see where I think here is the desert. Here is the plateau, right? So the deserts are here. So there is a band of large deciduous trees up north. So a lot of this is dependent. We have to specify the plant functional height. So I don't know if I will go back and look at it and see because I think the deserts are here, but I'll check.
Yeah, in one of the slides you talk about the lower red area.
Yes.
Can you go to this? Yeah, I noticed the southern tip of the South America.
Yes.
The color is different from the rest of it.
Yes.
Do you have an explanation for
No. No, I said that these are the figures I'm trying to understand what happened. And so this is from the model, so I should be able to get, this is not the observation. So we really struggling with this figure. Because this figure is basically the whole story of the drying and wetting and where does it dry and where does it, all of that. I have no explanation.
not those?
That's very strange. Yes. Yes.
For the recent IPCC assessment report number 4 that's released on the 2007, I think none of the model has been using this kind of interaction on the climate and carbon.
That's only in chapter 7.
Right, but
not the rest of them.
So I'm thinking, of course, on the next one they are preparing for the assessment report number 5.
Yes.
The year 2012. Yes.
Yes.
So what do you project, this kind of carbon and climate study model would be a kind of a mainstream?
Yes, it will be. Yeah, yes, this is why we're nervous. This is why we're very nervous.
Yes, but my point is from the comparison you are doing now, the result showing from the comparison from the carbon climate interaction the model, I think the range of the deviation is quite large.
Yes,
so
but
compromise on that one.
But we are trying to figure out how do we do it so you normalize to a standard climate first. Okay, so there's nothing I can do about somebody else's simulation of precipitation or climate sensitivity. So this is why we look at, I will show you later, where we actually do the analysis where you separate out from the uncoupled one, what is the feedback of the terrestrial system to CO2, what is the feedback of the ocean system to CO2, and what is the climate sensitivity, and how do you normalize all of that. So this is why we run a lot of runs to do, if you will, partial derivatives and not compare total derivatives. So we're still working on the protocol for the 5th one and what runs we will do, but we have to have the model ready by 2008. Which is very soon.
So that leads to my other question, because I noticed you have another affiliation with the policy science and
yes.
So what I'm thinking, because the climate problem is one of the science and policy,
yes.
the global change issue, one of the very good example for the science and policy transitions. So from this kind of new result, what do your prediction or assessment what kind of new climate policy would be imposed?
live in a new country called California. Okay, where there's a President Schwarzenegger. But California has, the governor has committed to 80% reduction of CO2 emission by 2020. Okay, forget about the rest of the U.S. The UC Berkeley campus has committed to reducing the CO2 emission by 80% in 2014. Okay, 6 years ahead of the state. So what we're doing is to say, how do we do that? Okay, new energy sources, new building materials, insulation, reduction, less wastage, more energy. There's a large group working on new materials. There are groups working on synthetic biology, the new fuels, hydrogen fuels, and other fuels. But there's also so that's at the production side. Okay, there are groups that geologic carbon sequestration, they suck CO2 out of the air, put it back in the mines, and other things. But in terms of, so a lot of action is going on in California, and so it's very exciting to be part of that. The students are very much involved in tracking which building turns out lights, which building doesn't turn out lights, all the electricity. We have monitors for various buildings. We're trying to pay for more monitors for all buildings. But from the modeling perspective, well, the next generation is one thing to say this is we do improvement for the next IPCC, but we're talking about a new generation of models that would be useful for testing different strategies for managing CO2. Okay, so different, what is the climate? If you grow sugarcane for fuel, corn or sugarcane for fuel, that changes the hydrologic cycle, that changes, okay, the albedo, that changes a lot of things. Okay, so what are the climatic consequences of those? If you use, what is not in the models at the moment is if there's warming in the tropics, we expect more air conditioning use. Okay, so how would that feedback into this, etc. So different energy scenarios. So we're talking about a new generation of models where we incorporate, traditionally difficult, human behavior. It's really tough to write equations for human behavior. Different elections, the whole thing changes. So we're trying we are talking about what is a new kind of model that's interesting scientifically, but also useful for decision. So obviously what I've done, these huge things, long and high resolution, is just too expensive for that kind of thing.
Yes.
In your conversation is the CO2 exchange impact a very important issue for research and long-term operation.
The CO2
exchange impact.
Yes.
Exchange rate.
Yeah. Yes. That's the whole thing. The whole problem is a problem of time. Okay, what is the time constant for the leaf litter, the decomposition of wood? What is the time constant for exchange between the surface, between the atmosphere and the mixed layer? The time constant for the exchange between the mixed layer and the deep ocean? Everything is a matter of time. Okay, so if there's enough time, then the ocean, the calculation is that the ocean can take up maybe 15%, maybe 80% of the fossil fuel CO2. But you don't have the time, right? If you wait 5,000 years, okay, stop emission and wait 5,000 years, the ocean can do that. But the emissions are going up much faster than the oceans and the land can take up the carbon. That's how it is.
I wonder, have you compared the tropical storm patterns on your simulation with
Storm.
tropical storms?
Well, I wouldn't do it at this resolution. I wouldn't dare do set this resolution.
The reason for this is because in the recent issue of the paper published in Nature, the people they are talking about figuring that the ocean mix used by the
Yes, I'm aware of that. So that process, I would answer it in a different way. That process is in the model, okay? But at the resolution I'm looking at, there's no way I can even tell you with a similar story. Okay, but that process is in the model. So when this is done, this is the first time that's done. Okay, so now the code is there. Now we can change the resolution. We can run it at at whatever resolution we want if I have computing time. Then we can look at those processes. Okay, so at the high resolution, the handling model, the ECMWF is run at T500 times. I'm doing T41 here. But I run 1,000 years, okay, and they run weeks. Okay, so there's a major difference there. So it would be useful to run this, now that we have the whole thing running, it's stable, at least many of the bugs are out. Okay. And then now we can run it at 100.
同学们有个问题啊，可以用中文问。Good question. In your model, do you consider do you have aerosols in your model?
Not this one. The next one definitely has aerosols. The next one has all the aerosols. We have the sulfates, biomass burning, BMS from the ocean, forming as carbonization nuclei. We're doing volatile organic carbon emissions from plants and then secondary organic aerosols in the atmosphere. A large range of aerosols. But knowing, it's one thing to say we have aerosols, but it's another thing to say what are the properties, the radiative properties of the aerosols. So we have dust in the atmosphere, and the calculation of what climate, whether the dust will enhance precipitation or not, depends on the single scattering ability of the spectral characteristics, of the aerosols. And there's very little known, so it's one thing to say with aerosols, I don't know the size distribution of aerosols we should have. Okay, so everything that we have sort of matches what we think the optical depth is being used from the satellite observations. But when you go changes, then you say, can I do this? Can I predict changes in aerosol? We can do it, but how good it is, we really need observation.
Another ask a question about, more related to my career, that is how important the ocean is in your model, especially biochemistry model of the ocean. How sensitive is climate to biochemistry?
Well, this is what I just showed you, is that the ocean takes up 25, right now the oceans take up 25 or so %, a quarter of the CO2 from fossil fuel. So the ocean will take up less, and if the productivity is decreased, and if the biology decreases, as we show, then the ocean will take up even less.
Yeah, that's what the ocean behave as it is, more or less. Do you expect any surprises from the ocean? Maybe you will.
I'm always, but in this thing, one is always prepared. One is like, is it, when the CO2 goes down like this, is it going to turn around? Is it going to keep going? Okay, so one is always like, what surprises are in store for me? When the whole thing crashed, and then that was, so there are large variations. I didn't show, but the 1,000-year run, I have multiple time scale of natural oscillation in the ocean. I have centennial scale oscillations in the ocean. And the centennial scale, when I look at the standard deviation of sea surface temperature, on the centennial scale is centered in the North Pacific. So we're trying to understand what is going on in the North Pacific, okay, that happens centennial time scale. So this is a rich data set. There's 1,000-year run, a rich data set of two. Not to say simulation, but think about it as a theoretical framework. Okay, expensive box model. Okay, where we can look at that. Let's say how the processes are interacting, rather than it's just a simulation. It's a good simulation. You know, it's a reasonable simulation, but there are many things that are not.
So you have 2,000-year run, right?
No, 1,000.
1,000 years.
Yeah.
I mean, that's from 2000.
No. So I have 1,000-year run that has no, so the CO2 is held at 280 parts per million. And then I have many runs from 19th, 20th, 300-year runs. So that's testing different hypotheses.
还没有问题。